All right, let's get started. All right, PS1 is due today and tomorrow. PS2 will come out soon and be due next week. Any questions or problems? Right, I have a couple questions. So there's I can look at the queue on Caddis and see every submission and how many were got right and when they were submitted and who they were submitted by, and I can look at why things were wrong and I can see everything. So let me tell you a couple things that I see. You tell me what. I'll ask you a question about it. So one thing I'll see is repeated submissions by the same student. This happens not just one student. Lots of students do this. I'll see submission, 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 minutes apart each submission. Same number of mistakes each time. Like pass two, pass two, pass two, pass two, pass two. So if what sort of debugging technique is that an example of? Obviously the program's wrong, but what's the debugging technique at work here? Yes?
Guess and check.
Guessing, yeah. Guess and check. This is not a very effective way to use your time. I see this every time I teach this class, and it illustrates to me a refusal to create your own test cases. Okay, you cannot debug your program in any effective way against test cases whose results, you can see the results, I guess. You can see whether you pass or fail, but you can't see why. Right? You can't step through. You can't set breakpoints. You just can't do it. So I really, really encourage you to, when you get in that situation and you don't know what's wrong, you've got to create a test case of your own that you failed. Then you can fix your program. But guessing just isn't going to get it done. Yeah.
So when it comes to the Caddis is timing, does it also time in getting from standard and all that?
Oh yes, yeah. The timing for Caddis, there's an amount of time you have, first of all, for all the test cases to run, and it definitely includes the input-output. And I have seen students write a perfect algorithm and screw up the input-output by making it so inefficient they run out of time. So the slickest algorithm in the world ain't going to help you if you write an n-squared input algorithm. The most common way people do that is they'll read a character. They want to build a string, and so they read a character and append it to a string. Another character, append it to the string. Another character, append it to a string. That's n-squared loop right there. So yeah, input matters. Okay, so that's one thing to take to heart. The other thing is I have looked again on the queue for this problem, and again, this isn't the first year I've noticed it, and I see lots and lots of failed submissions where the two test cases that are given you, the very simple test cases, are passed, rest are failed. And every time I look at the program, I see the same mistake. And I'm sure some of you sitting here have had that mistake and you fixed it. So I don't need you to answer. I'd like other people that don't know the answer necessarily to speculate. What mistake is everyone making that they can, not everyone, but a lot of people making, where they can pass the first two test cases, but they consistently fail the rest? Yeah?
Printf statements?
Say what?
Printf statements?
Well, okay, printf statements. So if you put extraneous prints in your code, you're going to fail the test cases. That would make you fail the first test case as well. If you put extraneous output, yeah.
For mine, it was the taking in the n and the k, where at first I thought it was just a single digit, and you have to take in double digit.
Exactly. So the code I see to parse the n and the k out is the code will read the first character, it'll read the first line of input as a string. It'll take the character at index 0 and parse that as an integer. And sometimes it'll take the character at index 2 and parse that as k. And that works on the first two inputs because both n and k are single digits. Okay? So I just saved some of you a lot of time. Okay? But the other cases are bigger. And right? So you got to parse ints, not as characters. And again, this is you would have caught this problem if you just written a test case that used a reasonable amount of data. For this problem, it's not that hard to come up with test cases. You just put a bunch of words on a line and count how many there are and put the number at the top. Now, some people that made this mistake, they weren't parsing out k because you don't really need k. Right? K doesn't really come into it. And so they just read n as a single digit, and then they would fail by failing the test case, producing the wrong output. Folks that were trying to read k as well as n this way, what do you think happened to their code when it ran? What would happen if there's a 2-digit n followed by a space followed by a k? And you're looking, yeah.
Well, it would get an error. It would throw an exception because
Right.
you're reading that space and trying to parse
You
it.
get a runtime error because you're trying to parse a space as a digit. You're trying to convert a space into a number. So I saw both varieties where pass the first two cases, just fail the test case, pass the first two cases, get a runtime exception. Okay? So this happens a lot where the problem with everyone's focusing on their algorithm and forgetting about the input and output. The input and output can be really straightforward. It should be really straightforward. Just you just need to read as ints, not as characters. Okay? Any other questions or comments? Okay. All right, we're going to continue. This is our last day of reviewing. We're going to spend some time talking about data structures from, you should know from previously. So we'll start talking about a list abstraction. A common abstraction that you use in your programs. And so a list essentially is a collection of elements indexed with integers. And the common methods that are provided for this are a get or set method that either obtains or changes element at a given index, an add last or remove last, something to add or remove at the end. There'll be a way to iterate through the list, and as you're iterating, there'll be a way to get or set or add or remove at the iteration point. Okay? And almost all languages provide something like this. What's Java provide like this? What's that?
Just the
Array list is one. What else? Linked list. Okay? What about in Python? Python have something like this? C#, C++, in the standard template library? Yeah. And you might say arrays. Arrays are sort of like this, but they don't really provide, they provide the random access part, but not the adding and removing at the end part. Okay. So there are two common ways to represent a list like this. One is a dynamic array representation, and that's like an array list in Java or C#. And the idea is, you've seen this before, is to represent internally, inside each array list object, you have a fixed length array. But the fixed length array has room to grow. So what I've got here shows an internal array of size 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So internally there's an array of size 10. The dynamic array itself, the abstraction, the array list, only has 6 elements, and they're stored in the first 6 spots of that internal array. And so the unused spots there are used, it's just room to grow. So the subsequent things are added, that space is used, and when that space fills up and we need more space, we have to allocate a new array that's longer and copy the old elements over. So every now and then, adding to the end will take a long time. Most of the time it'll go fast. Every now and then it'll be really slow. So that should be familiar to you, how array lists and the like are represented. But I want to make sure everyone understands. So does this make sense? Is this familiar to you all? Okay, well, let's analyze it. So I want to get at the best case and the worst case for all these operations. So what about the get operation? Okay, so in the best case, that's constant time. We just go to where we need to go, to the index that we need, because we just index directly into the array and get that thing. What about the worst case? What's the worst case for a get operation? Well, I heard constant, I heard in. What do you think?
Where it is,
Hmm?
right? So we have to check each one. Like it's not like get at it. So we have to go iterate through the list.
No. Get. Let me go back.
Am I being dumb?
Get and set take an index.
Oh, okay.
This isn't a search operation. We're not searching for anything. We're yeah, it's still constant.
Comprehension skills.
It's always constant. So the best case, the worst case are both theta of 1, which means that the operation itself is theta of 1. Right? What about adding to the end of a dynamic array? So we're just saying a dynamic array, add a new element at your end. Okay, in the best case, that's constant. In the best case, there'll be a space in the internal array for it. In the worst case, we'll be adding to the very end, and we'll have to double and copy. So what's the complexity there? Okay, it's linear. What's n, though? What's n a measure of? Okay, you hear one person. What's n? The number of elements in the dynamic array, or in the array list, however you want to think about it. Yeah. So in the worst case, we got a linear time insertion. Add to the end, rather. Okay. Now, when I say there are operations provided to iterate through the list, I don't mean writing a for loop that generates the indexes and do it that way. These abstractions, like array list, provide like a list iterator object that you can use to access the list. And the advantage of using a list iterator object is, as you're iterating over the list, you can insert, delete, change as you iterate. Typically, you can't do that. You get a concurrent modification exception in say, in Java or C#. But if you use the list iterator provided by the object, you're allowed to, you've got limited way to modify the list as you're iterating over it. So what is the cost of iterating over a list? Just suppose you use one of these list iterators to go through the list and print out the elements. What's the complexity of that? Now, that's going to be linear as well. So that's efficient. As you're iterating, so think of my finger as pointing at the thing you're currently accessing. When you get to that point, so I'm not counting the cost of getting there, but once you get there, what's the cost of obtaining that element? Yeah, that should be constant time, because my finger would just essentially be an index. So we get constant time. And now suppose that as you're iterating through the list and you're pointing at an element, you decide to insert something at that point. So that means we've got to move everything to the right over one slot and put something right there. So what's the best case for this? Constant. All right. Now, what's the worst case? Well, it's certainly linear if the array is already full and we have to copy it. But what's another worst case? Yeah.
If you have to add it at the very first element and then copy as well.
Right. If you have to add the very first element, he said, and then copy as well. We'll separate the two cases. Even if the underlying array isn't full, if you have to insert at the beginning, you're going to have to copy every element over to the right. Even if that doesn't trigger having to make a bigger copy of the array, that would truly be the worst case. But even in that situation, even if we insert at the beginning of this one up here, it would take linear time because we'd have to make room to put the thing we wanted to put in. So that's a linear time operation. Okay? Hopefully this makes sense to you. But if not, yeah, questions? Yeah.
You don't have to account for that worst case where it also copies it?
Okay, yeah. Yeah, I mean, that truly is the worst case. So what would be the cost? Suppose this thing were already full, and we have to insert and then copy, or copy and then insert. Still be linear. It'd be slower, but it's asymptotically it's the same. Any other questions? Okay, so that's dynamic array. Right? The other option that's commonly used is a linked list. and often a doubly linked list. And we are assuming that what the object contains is it knows the size of the list. It contains a reference to the first element, that node containing 5, and it has a reference to the last element, that other node containing 5. And then we got the usual operations. So in this case, insertion doesn't involve copying, it just involves a little bit of list surgery. So to insert, we have to create a new node, that 2, and link it in, move a few pointers around and link it in. So that's a fast operation compared to doing all the copying required for an array list. So let's think about this. Someone gives you a linked list and says, give me the ith element. Okay? In the best case, how long is it going to take to find that element, to obtain that element? Yeah? Right, that's constant time. What about the worst case? So what is the worst case? If it's right in the middle. If it's right at the end, you can go to the end and work backwards. If it's at the beginning, you can go to the beginning and work forwards. Worst case is if it's in the middle. You're going to have to go through half the elements to get there. So that's linear time. What about adding at the end? Yeah, that's always constant because we're assuming we're holding a reference to the last element. So we can just go straight there, add on to the end and be done with it. So that's good. What about the cost of iterating through? So now, again, the language provides a list iterator that will take care of walking through the list for you, which basically means it's following the links. So what's the overall cost of iterating through a list? Again, printing all the elements out as you do it. Yeah, that's still linear. Okay, as you're iterating, the iterator has its finger on a particular element, like that 3. What's the cost of getting the 3 out? That's constant. So I'm separating out the cost of getting to the spot and the cost of doing something once we get there. But once we get there, actually extracting the element's constant time. And what about adding an element at a spot? Yeah, again, constant time. Okay, so that's the linked list. Any questions about that? Yeah.
Can you explain one more time why the worst case for get is linear and not like log event? Since it's only half of the elements, not all of them?
Okay. Logs show up when you divide something in 2 repeatedly. But, okay, imagine there's a 100 element list and we've got to get the thing at index 50. So we've got to look at 50 elements. So that's n over 2 elements.
Okay.
Right? It's not log n, it's n over 2, which is same order of complexity as n. Yeah?
Are your get at and add at, are those iterator methods? So I don't see the difference between like get and get at, but if that's just...
Yes, typically a list iterator, say in Java, which I'm most familiar with, the list iterator object provides methods just in that iterator object to modify and obtain the element and insert or delete even. Yeah. So the difference is get at and add at are operations on the list iterator object, whereas get and add last are operations on the list itself. Any other questions? All right, let's compare this. So what I've colored red the places where we disagree, where the not where we disagree, where the implementations have different complexities. So generally speaking, the dynamic array is better at random access. So that top line, the get, is constant time always for the dynamic array, but it's linear time for the linked list. On the other hand, linked lists are better at insertion, and you can see that on the add last line. And an add at time. I guess it's more like, look at the add at time. That's the one I really want to focus on. That's you see the difference there. But I'm going to argue that that other theta of n on the add last line is sort of a pessimistic way of looking at what's going on. It's really not so, adding to the end of a dynamic array is really not so bad. And saying that it's O of n is misleading. So I want to get a handle on that. So what we're going to do is what's called an amortized analysis. And you'll see what it is once we've done it. Instead of analyzing the worst case for a single add last, I want to look at the worst case performance for k consecutive add lasts. So amortized means we're essentially averaging over a whole bunch of operations. So what I want to show you is that, yeah, an individual operation can be a disaster in terms of time. It takes a long time. But there's so many fast operations before you trigger a slow operation that it averages out to a constant time. So this is what we're going to assume. We're going to assume that the dynamic array internally will have room initially for one element. We're going to, as soon as our internal array fills up, we're going to double it. And that's slightly worse than what happens in reality. In reality, you don't double when it fills up. You double when it comes time to insert something and it's already filled up. So we're going to do it a little bit earlier, which will make our analysis a little more pessimistic than happens in reality. And then we've got to have some way of accounting for costs. So we're going to count the cost of adding to the end, an append operation, adding to the end of a, I guess that's what I called add last in the other slide. I don't know why I said append here. But an add last cost has cost A. Well, okay, I see, never mind. Add last is a whole operation. One thing you have to do in add last is stick an element at somewhere in the internal array. We're going to say the cost of that is A. That ought to be pretty quick. The other thing that might happen when you do an add last is you might have to double and copy. And the cost of that we're going to call R per element. So if you have an array with 8 elements in it and it's full and you got to double it, the cost of doubling it is 8R. You pay a cost of R for each of the 8 elements. So we're going to try to figure out the cost of doing K insertions, K add last operations. We're going to try to get the average cost in terms of A and R. And then we'll see that it's a constant. And we're going to, if I did an analysis and I said, okay, let's insert like almost, 1 million elements until we're just before doubling and then we'll stop and compute the average. That's going to come out as a lower average than if we went one step further and triggered the doubling. Then the average would go up a bit. So we're just going to analyze, we'll look at K's that are powers of 2. We're going to insert so that we trigger the worst case behavior. The last add we do, the analyze is going to trigger a doubling, just to make sure that we're as pessimistic as we can be and get a true upper bound normals. Okay, and the rest is just counting. All right, now I want to pause before we start counting and make sure you understand how I've set up the problem here. And have a couple of observations to make while you're thinking of questions. One is that there'll be a problem on the next assignment on PS2 where you're going to repeat the analysis I'm doing here, but you're going to analyze a situation where instead of doubling the array each time, you triple it each time. See what difference that makes. So it's important to understand what's happening here, because you'll have to do this yourself. The other is, this is exactly the way that it used to work in an array list in Java. They would start with some initial size, not necessarily 1, but they would double each time it filled up. And a few years ago, they stopped doing it that way, and they started, now they do a little bit less than double. And the reason they do that is, it's still, you get a constant time average, but it allowed them to make better use of, it was easier on the garbage collector to do less than doubling each time, like maybe go up by, instead of increasing by 100%, increase by 90%. I don't remember the exact details. But that's something we're not even thinking about, is the effect this has on memory, because every time you double, you leave a hole in the heap, and it has to be dealt with somehow. Okay? So any questions about this setup here? Okay? Just as a warm-up, so remember what A and R are there. A is just a garden variety, stick a number in an array, and R is the cost per element of a doubling. So let's, before we start counting, this is the internal array, let's say. We'll give it 4 elements. Suppose we do insert, add last, add last, add last, add last. Now, under the assumptions that I've just given you, except we're going to start with an array of size 4 instead of an array of size 1. What are all the accrued costs here? Remember, A is the sticking something in the array, and R is the per cost of doubling, the per element cost of doubling. So what would be the overall cost of this? I'll go back. I add last, and the element goes right there. What was the cost of that? That's an A. I add there. What's the cost? That's A. I add here. That's an A. I add here. That's an A for that, plus I've now got to copy each element to an array that's 8 long, and that's the cost we agreed for that's 4R. So this ends up being 4A plus 4R if we do it that way. That would be the cost. Now, let's try it a different way. Let's say we start with a 1-element array, and we do an add last. What's the cost of that going to be? So we stick something there, that's A, plus now we have to copy it to something twice as big, so that's an R. So now we have something twice as big with something in it. Now we do another insertion. What's the cost of that going to be? We go to here, so that's an A for the adding, and then 2R for the copy that's coming up. And we're here. We do 2 more, and then that's going to trigger a 4R. So if we add that all up, it's what? 1, 2. It's 4A plus, is it 7R? 7R. Okay. So that's the accounting we're doing. So I'm about to show you a table where we're going to sort of count arbitrarily deeply, but I wanted to warm you up by showing you what we're doing here. Okay. Okay, so here's my table. So in the left column, I have operations I'm doing. And then in the middle column, I show, at least on the shaded rows, I show the ending size after that operation. And then I give the cost. So I start with an initially empty dynamic array that internally has a 1-element static array. We do 1 add last. So now our dynamic array contains 1 element, and that costs A, but that triggers the resize, and that costs R. And that's just like I showed you when I was scratching on the screen right now. So when we get down to, we get down to this point here, having done this resize, we could add these up, and that's the total cost, A plus R. Okay, now we have 1 element in our internal array, in our dynamic array, and our internal array has room for 2 elements. So it's going to take 1 more add last to fill it up to give us the ending size of 2. That's another A plus a 2R for the copy. Okay, now we have an array of size, a dynamic array of size 4. It's going to take 2 more adds to fill it up, giving us 4 elements total, 2A plus 4R for the copy. Right? So far, I've just repeated what I did before. And you can see our sum there is like 4A plus 7R like before. Let's see. So at this point, the internal array has room for 8. It only contains 4, so 4 more add last will fill it. That's 4 adds and the resize is triggered. Now there's room for 16 and only 8 elements, so 8 more add lasts will give us a size of 16. It'll trigger a doubling, so 8 adds were done, 16R for the resize. And so now you can see the pattern that's happening. Except for these, this up here is kind of an outlier, but otherwise we're going, this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So in general, let's suppose we keep going for some k. We go 2 to the k add last. So we do 2 to the, suppose we end up, imagine dot, dot, dot. It goes 8 and then 16, 32, 64, 128, 256, 1024, maybe 2 to the 10th. Okay, on that line, what will the ending size be after we do the final 2 to the k add last? Yep.
2 to the k plus 1.
Okay, 2 to the k plus 1. Where'd you get that idea?
Well, we see that the ending size is double of the previous, which is just multiplied by another 2.
Right. So you see the pattern here. This is 2 to the 0, but this is 2 to the 1. This is 2 to the 1, but that's 2 to the 2. 2 to the 2 goes with 2 to the 3. And there are other ways to see it, but that's it. It's 2 to the k plus 1. That'll be the ending size after you've done all those insertions. And what's the cost going to be? Somebody else tell me. What's the cost in terms of a's? Yeah?
2 to the KAs.
2 to the ka, because you see that pattern up here. Like 4 add last cost 4a. 8 add last called 8a. So it makes sense that it's going to be just 2 to the k times a. By the way, I realized seeing this that I said we were going to talk about doing k insertions. And then I went and used k for a different purpose here. So this k is different from the k I was talking about before. Great. And then someone else tell me what will be the resize cost. Right, it's going to be 2 to the k plus 1 times r. It's just the, you're just following the pattern. Okay, so we have accounted for a whole bunch of adds. In fact, how many elements did we insert into our dynamic array? Where's the answer? The answer is in the table. Yeah?
16 total?
No, I mean all the way down. Imagine a dot, dot, dot between the 8 add last and the 2 to k add last. What's the total number of add last operations that we did to get down to this point down here?
2 to the k plus 1.
Right, 2 to the k plus 1. It says right there. Our ending size is 2 to the k plus 1. We inserted 2 to the k plus 1 elements. So that's the ending size, so we had to do an insertion for an add last for each one. Okay, so how could we compute the average cost for a single insertion under these assumptions? You insert up until you hit a power of 2. How do you get the average cost? Yeah. Right. We add up all the costs on the right, and you got to remember there's some costs that aren't shown. Remember, there's the implied dot, dot, dot going on. And then you divide by 2 to the k plus 1, which is the number that we inserted. And so we want to see that. My argument is that's going to be a constant. All right. So let's do it. So the cost of the add last. So we're just going to add all these costs here in the shaded, the darker rows. So the first one I said was an outlier. So that's A. And then the rest follow a pattern. 1a plus 2a plus 4a plus 8a plus 16a all the way up to 2 to the k, a. So all I'm doing is adding that, and so on, and factoring the a out of this. How do we simplify that? Okay? So I told you it's good to know that the sum of the first k integers is what? K times k plus 1 over 2. That's good to know. It's also good to know that the sum of the first k powers of 2, which is what I have here in parentheses, is, well, let's think about it. What's 1 plus 2 plus 4? 7. That's 1 less than 8. What's 1 plus 2 plus 4 plus 8? 15. That's 1 less than 16. So the rule is if you sum the first k powers of 2, the number you get is 1 less than the next power of 2. In other words, it's 2 to the k plus 1 minus 1. Right? Handy fact just to know. So that tells us that this stuff in parentheses adds up to 2 to the k plus 1 minus 1. 1 less than the next power of 2.
2 to the k plus 1a.
Okay? With me so far? And that, of course, simplifies to just 2 to the k plus 1 times a, because you got an a and a minus a, so they cancel out. So that's the cost of all the add lasts. Now, on your assignment, I mentioned you're going to be doing this analysis for tripling. You're going to have to end up adding powers of 3. And there the rule isn't the 1 less than the next power of 3. But I think I tell you the rule in the assignment, or it's easy enough to look up. There's a general way to solve sums like this, though doing powers of 2 is particularly easy. Or at least particularly easy to remember. None of them are particularly hard. It's just easy to remember this one. Now we've got to add up the cost of all the r's, the resizes. And you can see that's just 1r, 2r, 4r, 8r, all the way up to 2 to the k plus 1r. So that's the sum right there. And again, that's the sum of the first k plus 1 powers of 2. So what's that sum going to be? 2, the next power of 2 would be 2 to the k plus 2. And then we subtract 1. 1 less than the next power of 2. So 2 to the k plus 1 minus r still times r. So those are our costs. We need to add them up. So I've just taken the 2 to the k plus 1a plus 2 to the k plus 2 minus 1 times r. And let's see what I did with it. I'm just simplifying. You can verify my, okay, that's what I simplified it to. So it's 2 to the k plus 1 times a plus 2r minus r is what the algebra tells me that is. All right, so that's the total cost. So to get the average cost for all these insertions, what do we do? We divide it by the total number of add last we did, which is going to be this ending size, which is 2 to the k plus 1. And that's what we get. Notice that when we divide this thing here by 2 to the k plus 1, we get the a plus 2r term right here, minus r over this. Now, if we just ignore this, it's clearly constant time. A plus 2r is a constant. But what about this? This seems to confound things. That minus r over 2 to the k plus 1.
As k increases, that'll approach 0, so
Yeah.
it's not the dominant factor.
All right, that's a lower order term. Lower order even than a constant. As k goes up, that quotient goes down. You know, r stays the same. The denominator gets bigger and bigger and bigger over time. So in fact, the more adds you do, the lower the average cost becomes. At worst, the average cost is a plus 2r. Okay, so that's the argument that you can do that, yeah, in the worst case, it takes linear time to add to the end of the dynamic array. But if you average over all the adds that it took to get there, to trigger the worst case, it averages to a constant. And that's why array lists work so well. Except in certain situations. What would be a situation where you really would care, not about the average cost of insertion, but you actually care about the actual worst case taking a long time? Yeah?
Adding at the start all the time?
Say again?
Adding at the beginning of the list all the time?
Okay, I don't mean when I mean an example, I mean a real world application where you'd be using a program to do something and you would worry about some operation occasionally taking a very long time. Yeah?
Like real world media recording, like you're taking a video and the last frame takes way longer than it should.
Okay? So if you're taking a recording and every power of 2 frame for whatever reason triggers this copying and the real-time constraint's not met and it drops the frame, you'd get it. That would be no good. You don't care that on average the frames are created at constant time. Periodically one is dropped. You don't like that. What's another example? Yeah?
You have an operation for like a motor controller and you keep adding to the beginning of it and all of a sudden it takes too long.
Okay. So you got a microprocessor controlling your car, and every now and then the steering fails for for a millisecond or whatever because the insert took too long. Or you've got software controlling a nuclear power plant, and every now and then it melts down. So the usual argument is amortized analysis is fine if what you're interested in is a total running time of some program. But if you have real-time constraints, then this isn't analysis you want to do. Okay, so like I said, you'll be running with this on PS2 and doing a similar analysis, and it's not that hard. You can follow the same pattern. But what can make it hard is if you don't understand this. Right? If you understand this, doing it for tripling isn't hard. If you don't, it is hard. So I'm happy to explain things if you don't understand. Yeah?
I'm just curious what you mean by tripling. What is tripling precisely?
Okay. So we made the assumption that when the internal array fills up, we double it and then copy everything over and proceed. What you'll be assuming is you triple the length. So if the internal array contains 3 and it fills up, the new one contains 9.
Okay.
So the effect of that would be the tripling would happen less often than doubling, but the doubling would be, each tripling would be more expensive. Now, what is it about this that makes the average time constant? Because the costs keep getting larger and larger. You know, that doubling that happens when there's 1 million elements in the array, roughly, and it doubles to 2 million, is really expensive. So how can we withstand that? Yeah?
As the array grows, the number of add lasts that we have to do to get to the doubling also increases.
Okay, so what he said was, yeah, each successive doubling is more and more expensive, but it takes longer and longer to get to that point where you have to do the doubling. And if you double at 1 million, it's going to take 1 million more add lasts before you have to double at 2 million. And this trick works as long as you're increasing the size of the internal array each time by a constant, by a multiplicative factor, constant multiplicative factor. It won't work if you try to do a strategy where you say, okay, each time it fills, I'll add 10 more elements. That won't yield a constant time average. It's the multiplicative part. You'll get you won't get a plus 2r as the constant, you'll get something different, but
Get a plus 3r.
yeah, I don't think it's 8. Well, I don't remember what the answer is.
I almost got him.
Okay, so the conclusion is, okay, now here's where, see, I told you I messed up. This k I've been using an x as I've been using as an exponent is different from this k down here. I'm sorry about that. So read this as like m. M add lasts can be done in in theta of m time. And that brings us back to this table where you notice I changed the second row. Instead of saying add lasts, I'm saying k add lasts. So the deal is you can do k add last operations in theta of k time, which in many cases is a better way of describing what's going on than saying that the worst case is theta of n. And and the nice thing about this now is the symmetry between the two tables. We can clearly see dynamic array is better at random access, and linked list is better at inserting into the middle of the list. All right, let's take a break and we'll look at sets. All right, let's get started again. Okay, so our next abstraction that you spend a lot of time studying in 2420 is the set abstraction. And the set abstraction provides an unindexed collection of elements without duplicates. So that's, the difference is we do away with the indexing operation. You never ask what is the element in index 6 of a set. Okay. On the other hand, another difference is you don't have duplicates in a set. The operations you do have, you can insert an element into a set. You can remove an element from a set. You can look up an element in the set. And you can iterate through the set. Now, let me pose a question. Why would you why not just use a list? Because a list provides all these operations. Plus, it provides indexing. So why would you say, okay, I'll give up indexing? Yeah?
No duplicates.
Well, there's a new duplicate part, so sometimes that's useful. Yeah?
Isn't the lookup also constant with sets?
Okay. You said the lookup can be constant with sets, but it depends what kind of set you're using. But the point is, the lookup is faster. If you're using a binary tree, it's going to be logarithmic running time. A hash table is going to be constant on average. But the lookup is faster. Doing a lookup on a linked list or an array list is constant time, is linear time, because you have to search through for the element you're looking for. Okay. Now, does that come as news to anyone, that it's faster to look up things in a set than it is on a list? Okay? It doesn't come as news to anyone. But, again, looking at Caddis, I see a lot of solutions where students are using lists instead of sets to contain the anagrams. Okay? Now, there's no harm done if what you're doing, if you have a list of all the words you've got to deal with. Yeah, that's fine to be a list. But then you have those sets, things I called sets in my pseudocode, where you've got to say, okay, if it's in this set, you do that. Otherwise, you add it to this set, and so on. Your code will run a lot faster if you just replace those lists with sets. Now, unfortunately, I wrote that problem, and I screwed up because people are not running out of time when they use lists. Rats. I didn't make, so I'm sort of reinforcing the wrong lesson. I should have made one of the test cases bigger so that you'd run out of time, even if you were using C++, but if you use a list. But unfortunately, you're not seeing that problem, but you will in the future. So my point is, I think that some students tend to think of, they say, okay, I've got to learn some theory, but it has nothing to do with practice. But if little bits of theory can help a lot in practice. If what is called for is a set, you need to be able to recognize that fact and use a set, because it can make your program way faster. Try it out. Even if you've already finished a program, just go. There's no harm done in trying to make a modification. Just go modify where you're using a list, if you're using a list, and try out a set and see what difference the running time makes. Okay, so that's the set abstraction. So, two common representations that are used. One is binary search tree. So, you learned in 2420, a binary search tree is a binary tree, first of all. And the deal is every node in the left subtree is smaller, and every node in the right subtree is larger than the thing at the root of the tree. So you can see that constraint being observed recursively in this. So the 5 is at the root. Everything over here is smaller than 5. Everything over here is larger than 5. This subtree right here, everything over here is smaller than 2. Everything here is larger than 2. And so the fundamental operation you do in a binary search tree is you need to be able to walk the tree from root to leaf in order to get some things done. So let's see if you can remember how that works. So what's involved in looking up 9 in a binary search tree?
You look at the root.
Okay, you compare the thing you're looking up to the root. 9 is bigger than 5, so what do?
You go right.
You go right. So we start at 5, we compare it to 9, we go right. Now we compare the 9 to the 8.
So we go right again.
All right, the 9 can only be to the right, so we go there, and in fact we find it. Now, what about inserting a 4?
We look at the root.
Okay, so to insert something, you pretend you're looking it up. So you basically go to where it would be if it were in the tree. So we start at the root. We compare the 4 to the 5. It's smaller, so we go left. We compare the 4 to the 2. Bigger.
So we go right.
Go to the right. And then we compare, even though that's a leaf, we do a comparison. 4, if it were in the tree, would be to the right. So that's where we put it. So that's easy. And deleting is a little bit harder to illustrate, so I've left that out. But anyway, I think I left it out. Anyway, insert in the best case, inserts constant time. Okay, how would that happen?
Tree's empty.
Okay, the tree is empty, but even in a tree that's not empty, you can have a tree with 1,000,000 elements and still have a constant time insertion in the best case. So when we ask for the worst case, it needs to be a worst case for an arbitrary tree. The worst case for a tree of size n is what I want. Not what's the worst or best case for an empty tree. In general, what's the...
If you add to the root, you have to move a bunch of stuff around, don't you?
Okay, so it seems like if you try, how would you get constant time in a tree with 1,000,000 elements?
The depth of the trees, the complexity.
Okay, but tell me, describe a tree with 1,000,000 elements. Back behind you.
So it could be the only one bigger than the root.
Okay, so you could have this situation where your tree was completely unbalanced. And we go to insert, so maybe this is like, 1,000,000, something smaller, something smaller, something smaller, all the way down. 1,000,000 elements down this chain, and our insertion goes right here. That'll be a constant time insertion. So you can have a constant time insertion even in a huge tree. Now we're going to talk about balancing them, and then that will change. Now, years ago, probably 25 years now, I had a student that gave this on an exam, I think. He described this thing as a binary stick. And so the worst case for binary trees typically happens when the tree is a binary stick. I've been waiting around to see if the term enters common usage, and it still hasn't.
It makes me feel any better. I heard it in 2420.
Oh, it's got into 2420. Okay. I want it to go around the world or something. Maybe someday. Or what about the worst case for insertion into a binary tree, into a binary search tree? It's that binary stick
Binary
example.
bush.
If you had to go all the way down to the bottom, you'd be paying a linear time cost. Now, what about removing an element? Again, just think about the sticks. Well, no, I take that back.
Is it log n?
Well, I don't remember what I wrote. Constant time. What would it take to remove the root element of a binary stick?
Just remove it.
You basically just remove it, and what's left is what's left of the tree. So that would be constant time. What about the worst case?
It's the bottom of the binary.
You might have to chase all the way to the bottom. So the worst case is going to happen when you have to operate on the bottom of a stick, and the best case is when you do it at the top. What about looking up?
Constant?
Certainly, if you're looking up the thing in the root, that's constant. If you're looking up a thing at the bottom and it's completely unbalanced, linear. Then what about the cost of iterating through? So just like lists, sets have iterator objects that iterate through. So you have to do some sort of traversal.
Log n for best case?
Well, can it be log n, even if it's balanced? What's the simple argument that that you can't have?
You have to traverse the whole thing?
Yeah,
Yeah, reverse the whole thing.
you have to at least visit every vertex,
Got
right?
it.
Never mind.
Every node of the tree. So that's going to take linear time. And it turns out an in-order traversal takes linear time, no matter what the shape of the tree. Okay. Now notice I'm not saying the best case is theta of 1 for iterating and then saying it's the best case occurs when the tree has no elements. Okay? When we ask these questions, we want to know the best case in terms of n, in terms of the size of the tree. Okay, so that's that. Now let's do hash tables. So basically a hash table is an array of, well, there are various ways to do it. You can think of a hash table as being a generalization of an array where instead of using integers as keys, you're using other things as keys. And the way it generally works is, to make it work, we actually do use an array internally, and we map the actual keys that we're using to indexes into that array. So what I've done here is I've created, internally I have an array of 10 buckets, is what they're called. And I'm storing numbers between 0 and 99 in there. And can anyone recognize what hash function I used? Yeah.
Taking the last digit as the
Right, it's just the last digit of the key. So 50 ends in a 0, so it goes into bucket 0. 84 and 14 end with 4, so they go into bucket 4. That's not a great, it's not necessarily a good hash function. It could be, I guess, depending on the distribution of your data, but it's easy to present in class. Okay? So that's how that works. Now, what can go wrong with a hash table? Hash tables are usually, on average, again, very fast, faster than a binary search tree. How can a hash table go south? Yeah.
The single buckets list gets too long.
Right. If everything happens, one thing that can happen is everything hashes to the same bucket, and then that would be a disaster. And then we just got a linked list, basically. Okay. What else could go wrong besides everything hashing the same bucket? What if we've got a nice hash function that spreads everything out? Yeah?
Sometimes you have to increment your list size.
Yeah. He said sometimes you have to increment your list size. So the deal would be, okay, I've got that. If I insert 1,000,000 elements into that hash table right there, and the hash function's perfect, I'm going to end up with 10 linked lists of length 100,000. That's a linear time lookup now, because to look up something in the table, you got to go to the bucket and then search the list. And so what happens here is similar to what happens with the dynamic array. Once the load reaches a certain factor, once there's so many elements in the hash table, you have to stop, double the length, rehash everything, and then pick up again. And we could do the same sort of amortized analysis here that we did for dynamic array and show that it averages out, assuming you got a good hash function, it averages out the constant time. So let's do the complexities here. What's the best case for insertion into a hash table? That's constant. You may have to insert into a, like if I had inserted 99, it would be constant time, right? There's no, I just stick it there because there's nothing there already. What about the worst case? Of a hash table containing n elements.
It's just a chain.
Right, if everything hashed to the same bucket, we'd have to walk the chain because we can't allow duplicates. We have to go make sure there's not a duplicate. So linear. What about removing? Same deal. Look up, same deal. What about iterating? What would it take to systematically visit every?
Still the same? Still linear?
Well, again, it's at least linear time because you got to visit every node. There is a little additional cost, though. Yeah?
If you come to the length of the table too.
All right, the length of the table matters because imagine if you had 1,000,000 buckets and only one element. You'd still have to look in every bucket to find the one that contained the element. Okay, so if that were the case, we'd have to give the complexity in terms not just the number of elements in the table, but the number of buckets. But nevertheless, what I'm doing here is saying linear time because there are ways to add additional information to the table, basically chain the elements together. So imagine that this picture is exactly the same, except we had a linked list going that chained all the elements together, so that when you wanted to iterate through, you just follow that chain. You didn't have to look at the buckets. Right. It's possible to do that. I haven't bothered here, but it's reflected. That idea is reflected in this iteration complexity. All right, so that's hash table. So any questions I can answer about that, about hash tables? You got your choice. You need a set in your program. Should you use a hash set or a tree set?
Depends on your use case, right?
Yeah, it depends on your use case. What's the use case for a tree set? For a binary search tree backed set? Yeah?
If the data's coming in a shape where you're pretty confident it'll be balanced, then
Well, so the answer that he gave was if your data is coming in a shape that you think will make the tree balanced, but actually there are techniques to keep the tree balanced, so that's not really used in consideration. Yeah?
Use a tree for larger sizes.
He said use a tree for larger sizes. I don't think, I wouldn't call that the right answer either. Yeah?
I would say it's order matters. Use the tree.
Okay. So the thing about trees is when you do the iteration, when you walk the tree, you get the elements in sorted order. So if your use case involves, if you want to be able to obtain the elements in sorted order, maintain them in sorted order, but also easily accessed, you use a binary search tree. If that's not a consideration, typically you use a hash set, a hash table, because it's faster. On average, hashing is faster than binary search trees. Also, for binary search trees, your keys have to be comparable. There has to be some way to say less than. Is this key less than or that or larger? That might not be possible either. So I always default to a hash table unless I can think of a reason why not to. So if we compare these things, we can see that they look equally bad in this situation. Almost all the operations in the worst case are linear. So that looks bad. But they're bad for different reasons. Binary search trees are bad because the trees can become unbalanced. That's where all those worst cases come from. Hash tables suffer because everything hashes to one bucket. And also because we have to periodically double the size and rehash. Now we can deal with the doubling and rehashing the same way we dealt with the dynamic array, like I told you. Got to do something about the fact that it's possible for everything to hash to one bucket. So we're now going to see what we can do to soup up both of these things. All right, now, there are lots of techniques for creating what are called balanced binary search trees. And they operate by noticing in the way they differ is how they notice that things have gotten out of whack. When they notice how things have gotten out of whack, they all typically do the same thing. They perform what's called a rotation to locally improve the tree. Okay? Did you implement one of these in 2420?
Yeah.
Like red, black?
Yeah.
Okay? Pretty complicated, wasn't it? Hard, a lot of details to get right. So I'm not going to go over red, black trees. I just want to make sure that you understand the basic idea, what behind a red, black tree or an AVL tree or whatever you're doing, and that is the rotation to keep things balanced. So let's just do that and be done with it. So we're going to rotate 2 and 5. So right now 2 is closer to the root and 5 is farther away. And by red-black coloring or whatever, you decided that if we could make 5 closer to the root, then the tree would be more balanced. So rotation is pretty simple. So there's our yellow link. We're going to rotate around that link. So what I do is, well, you tell me, what do I do? I'm going to cut that link. And then, well, I already showed you. So we cut that link, and then we have it point to the root of 5's left subtree. Now, why does that work? How do we know that 5's left subtree, everything in it? So there could be, a big tree down here somewhere, hanging off of 3. How do we know everything in it's going to be greater than 2? Well, everything over here had to be bigger than 2 in the first place, so specifically these will be bigger than 2. So we do that. Now what do we need to do to the tree? Okay, this 5 to 3 we don't want anymore. We just remove it. And now what do we need to do?
Link 2 to 5.
We make 5 point to 2. Okay? Now how do we know that everything that 5 is pointing to is now going to be less than 5? Well, this used to be the left subtree of 5, so we know they're less. And we know this 5 is bigger than the 2 because it was initially a right child, and same thing goes for these guys over here. They're even smaller than the 2. So that's good. Okay, one more thing we have to do. We got to change the root. So we had that coming down from above before. Now we do that. Actually, there's one final thing we have to do. You got to grab that yellow thing and shake. And then you get that. And you can see it's more balanced. So this is the fundamental idea behind balanced binary tree strategies. The hard part is keeping track of the information you need to decide exactly when to do a rotation. Rotations themselves just involve a few swaps of pointers. Okay? So rotations are good. And it turns out that you can do these rotations as you're doing other operations without increasing their asymptotic complexity. It slows down the tree slightly because of the balancing, but it pays off big because it keeps things balanced. Okay, so with hashing, what you want to have is you want to have a good hash function. The definition of one is you want the probability that 2 randomly chosen keys that will hash to the same bucket is 1 over the number of buckets. So if there is 1,000 buckets and you pick 2 keys at random, the probability that they hash to the same bucket ought to be 1 over 1,000. That's what a good hash function is. And to make a really good hash function, if you publish the hash function, for example, if you know the hash function that's being used by a programming language, you can concoct a series of data to insert that will confound the hash function. If you know exactly how it's working, you can cause the hash function to start failing, being really slow, just by cleverly picking what you're inserting in it. And you can imagine that as a hacking technique. If you somehow knew what hash function some software was using and wanted to crash it, you could just fire exactly the right data at it. So what's often done in these things is that there's some piece of the hash function that's chosen at random when the hash table is created, so that every time it's different. Anyway, that's actually a fairly complicated topic to find perfect hash or good hash functions. But still, even if you have a randomly initialized, really good hash function, you still could get really unlucky. And our worst cases would still be linear. And so we just cover that up by focusing on the average case behavior instead. We just say, on average, this won't happen. These disasters are very unlikely to happen, so they won't happen very often. But they still can. So again, if you've got a really time-critical, real-time situation, hash table in that case might be the wrong choice, because it is possible that you'll hit a situation where it slows down dramatically. Okay, so this is our final comparison. On the left, I have balanced binary search tree. On the right, I have a hash table. And I've replaced the worst cases. Look at balanced binary search tree. Look at all the worst cases. They were linear. They were O of n, and theta of n. Now they're theta of log n. So how did that happen?
Well, it's no longer, it can't be a stick now.
Right. If it's all these worst cases came from binary sticks. Can't have them anymore if it's balanced. And now the worst cases, still the worst case is how long it takes you to get to a leaf. But now it just takes logarithmic time because the depth of a tree. If you have n elements in a perfectly balanced binary tree, the depth is log n roughly. It's not like, and by the way, these algorithms don't perfectly balance things. They get it close, but still the depth is on the order of log n. So the worst cases all become that. But we also had some best cases that got worse We had constant time insertion and removal before. Now they've become logarithmic. What's the deal there? Yeah?
You have to add in the complexity of balancing the tree.
Well, yeah, I guess that's true. You can do balancing when you're inserting, but there's also another reason. Yeah.
Well, it's the best cases also came from the binary stick.
Right. The best cases came from a binary stick. We said the best case for insert was you're inserting. You got a million elements, but they're all on the left, and we get to insert really fastly, very quickly on the right. So those two came from binary sticks. They aren't possible anymore. So to do an insert, you got to go to a leaf node. To do a remove, you may have to go to a leaf node, and both of those operations will take a logarithmic time to get to the bottom. And then over here on the right, where we have the average case, and we just replaced worst case with average case, and we see that on average it's fast. Now, what's the difference between the average case here and the amortized case that we had for the array list? Which gives you more of a guarantee on performance? Are they both sort of fudging? What's that?
Hash table's faster.
Well, I mean, well, we're talking about apples and oranges here, lists versus hash sets. But, yeah?
Will the amortized utilize the worst case when it was making this calculation? The average case does not assume the worst case. So the
Okay.
amortized would be more.
That's sort of getting at it. It said the amortized took the worst case into account. Average case is sort of averaging it away. Okay, even though the average case is constant time for these things, could you end up having to wait a very long time to do a lookup in a hash table if you got extremely unlucky? Yes, disasters are still possible. What about for the dynamic array? If you do k insertions, we argued that it takes theta of k time to do those insertions. Might there be a time when you do k insertions O and it blows up and it takes k squared time? No. The worst case is baked into that. So the amortized analysis gave us a guarantee. Any k insertions are going to take time proportional to k, period. There is no hidden possible disaster there. Certain operations may take longer than others, but it'll always average out to k insertions taking O of k time, if you're starting from an initially empty thing. With the hash table, yeah, on average it's constant, but there are you can't say anything like, okay, if you do k insertions into a hash table, it'll take O of k time, theta of k time. It may take, if you're really unlucky, it could take way longer. So the amortized analysis gives us a better ironclad guarantee about performance than just saying average case. Average case is hiding something. Okay, so that's where we are. And the fact that all these are logarithmic and all these average to constant is why we tend to use hash tables instead of binary search trees, but we've identified reasons when you wouldn't. And the real-time guarantee that you get over here, that you can't get over here, is one of them. Okay, any questions about either of those? Okay, there's one final abstraction, the map abstraction. And that's a lot like the set abstraction, except instead of just keys, there are values associated with each key. So like a printed phone book or a dictionary or something, where you have the key is the word and the value is the definition. And the operations there are very similar to a set. You insert a key value pair, you remove a key and its value, you look up a value associated with a key, and you iterate through the map. And there's really nothing more to say about it because the technology you use for a map is just like you use for a set. It's just got to be everywhere you store the key in a set, you would have to actually also store the value, but no big deal. So that part goes by fast. Okay? I'm not going to start a new set of slides with 5 minutes left, so we will end here.